here we're going to define something called a Taylor series of a function at A. And before we can define this, we must assume that f has infinitely many derivatives at A. In other words, it's infinitely smooth at A. If that happens, then the Taylor series of the function is given by t of x equals the sum from 0 to infinity of the nth derivative at A over n factorial times x minus a to the n. You can see how this expands. It's f of a plus f prime of a over 1 factorial times x minus a plus the second derivative at a over 2 factorial times x minus a squared, etc., etc. For this Taylor series, it's also infinitely differentiable, and it turns out that all of its derivatives match the derivatives of f at a. Now, if a equals 0, this is called the Maclaurin series because it was developed by Maclaurin. If you plug in a equals 0 here, you get the Maclaurin series of the function f at 0 is the sum from 0 to infinity of the nth derivative at 0 over n factorial times x to the n. So here we're going to show that all of the derivatives of the Taylor series of f at A actually equal the derivatives of f at A. Now, of course, it may very well be that the only place that this Taylor series converges is at x equals A. Certainly this sum, this infinite sum, has to be finite at x equals A, but there's no guarantee that it's actually finite for values of x close to A. But suppose it is, suppose there's some open interval around A where this Taylor series converges, then it's differentiable at A since it's a power series. And it turns out that every derivative of the Taylor series at A equals the corresponding derivative of f at A. Well, first of all, we can see that the 0th derivatives are the same. In other words, the value of t at A is f of A. And the reason for that is when I plug in A, all of the higher order terms disappear because they have an x minus a to a power greater than or equal to 1. And the first derivative of this Taylor series at any value of x is 0 for the constant term plus, when I differentiate f prime of a times x minus a, I just get f prime of a, plus when I differentiate the next term, I get the second derivative of f at a over 1 times x minus a, etc., etc. And when I plug in x equals a into my expression for the first derivative of t, I get f prime of a plus a bunch of terms which are all 0, because in the expression for t prime of x, they have an x minus a to the power of something equal to 1 or higher. So we get t prime of a equals f prime of a, and likewise, if we evaluate the second derivative of the Taylor series at x, then when we plug in x equals a, we get the second derivative of f at a, and we get that the second derivatives coincide, etc., etc. Our first skill that we want to learn is to actually write down the Maclaurin series or the Taylor series of a function. So let's find the Maclaurin series of the function f of x equals e to the x, and let's try to find the radius of convergence of that series. Well, we need to calculate all of the derivatives of f of x and evaluate them at 0. But of course this is easy because this is the exponential function, so f of x is e to the x, its first derivative is e to the x, its second derivative is e to the x, etc., etc. And when I evaluate all of these at 0, I get e to the 0, which is 1. So now, filling in the details for the Maclaurin series for f of x equals e to the x, I get f of 0 plus f prime of 0 times x plus the second derivative of f at 0 over 2 factorial times x squared, etc., etc. And when I plug in the values for the nth derivative of f at 0, which are all just 1, I get the sum from 0 to infinity of x to the n over n factorial. So this is a very nice Maclaurin series for e to the x. Now, last day we actually proved using the ratio test that this series converges for all values of x, so its radius of convergence is infinity. And of course we have yet to show that it actually converges to the function e to the x for all values of x. There's one very important thing to note here, which will be very useful in solving problems later in this lecture. Because this series converges no matter what the value of x is, we have that for every value of x, the limit as n goes to infinity of the terms of this series must be 0. So the limit as n goes to infinity of x to the n over n factorial must be 0 for any value of x.